Hey everybody, welcome back to the Unstoppable podcast. I'm your host, Diana Chen, and I'm joined today by my co-host, Matthew Gould, co-founder and CEO of Unstoppable Domains. Today, we are back to talk more about scaling and L2s. If you haven't listened to our previous episode about scaling, we went through all of the problems that we're currently facing with scaling on the public blockchain right now. So definitely go back and listen to that. But if you're new here, Matt, can you kick us off by just giving us a little recap of some of the current problems that we're facing, like with gas prices and things like that?
Yeah, so the biggest problem for users right now is that it's very expensive to use some of the most popular blockchains. And when I say very expensive, it can cost, $20, $30 to send a transaction on Bitcoin, and it can cost up to $1,000 to play around with some of the smart contracts, even more in some cases for like minting a crypto kitty on Ethereum. And it's actually a industry-wide problem because whenever a blockchain becomes popular, then its prices of gas go up. So that's currently what's happening with users on blockchains today. So if we want to recap kind of a little bit about what we covered last time, a couple of things have been tried on making blockchains faster when Bitcoin first came out. And one was scaling by increasing the block size. And for a bunch of different technical reasons, that never really panned out. So we don't have ways to just put more stuff on Bitcoin and let the transaction throughput go through. So if you're thinking like, why is a Bitcoin transaction $30? Why don't we just raise allow people to put more transactions on the Bitcoin blockchain? For a bunch of reasons I don't want to get into because a lot of people on different sides have different opinions, but it just didn't pan out. So and then the other one was people thought maybe we could increase the speed of confirming blockchain transactions, and that would allow more transactions to go through. And that suffered kind of similar problems where just too much data to store. So that also didn't work. And we had to, and then what's been happening over the last 10 years, because the technologists have always known that scaling is going to be a problem on the blockchain, is they've worked really hard to figure out how can we only store the most important things on the main blockchain? Like, what do we do to reduce that size? And in a perfect world, make it so that it's doesn't continue to go up. Like the amount of data we have to store in the blockchain doesn't keep getting bigger, because that's going to push the cost higher.
For sure. And so can you talk a little bit about, just recap real quick. We talked about, the Ethereum blockchain, the Bitcoin, the Nakamoto consensus, and then we talked about zero knowledge proofs in the previous episode. Can you recap just those terms real quick so listeners are caught up to speed when we start talking about some of the state of the art solutions that we're looking at today?
Yeah, got it. So I like to think of three really important innovations in technology around blockchains and in the past 30 years. And the first one is actually zero knowledge proofs. And they actually happened in the 80s and 90s is when they first came out. But because blockchains didn't exist yet, there wasn't really a good commercial use case for zero knowledge proofs. And what zero knowledge proofs do is they allow you to guarantee the accuracy of a bunch of data without having to look at all the data. And so we're about to talk about ways of storing more and more information on blockchains in a smaller and smaller space. And you can conceptually kind of think, oh, wow, if there was some sort of technology that would allow you to know the accuracy of that data so that I know that the accuracy on the blockchain is correct without having to store all of that data, look at all of it, that would make it so that we could have more transaction throughput on blockchains without running into other problems on technology with bandwidth and storage. So zero knowledge proofs, that's the first bucket. And I think it's really cool. It's very, very hard math. The people who work on zero knowledge proofs in the blockchain space, they all have PhDs, right? And people like me who work on the technology that uses those, we talk to those PhDs and we sit there and we go, wow, that's actually quite complex. Thank you for walking me through that. And we're users of those tools, but I don't pretend to understand the complex math behind them. Now, Wikipedia actually has a very interesting article about zero knowledge proofs. And there's this great example about a circular cave. And it's a very strange analogy. Anyway, that's a really cool technology because they allow you to know that something is accurate without having to look at absolutely everything and have all that data. So zero knowledge proofs, 80s and 90s. Then the other really neat piece of technology after ZK proofs was Bitcoin and it's called Nakamoto consensus. And this was the big invention that allowed cryptocurrencies to happen. And it's a way for you to have a public data set that anybody can read and permission people can write to. And you can feel very confident about the accuracy of the data on that public data set. And that's exactly what Bitcoin does. And it allows you to send cryptocurrency around to each other. And so that was the first implementation of the Nakamoto consensus, named after Satoshi Nakamoto, the pseudo-anonymous inventor of Bitcoin, and implemented in Bitcoin. So that was the second big innovation. And then the third big innovation was smart contract blockchains. And this was Ethereum was the first one of these that came out and we really had generalized computation. It solved the halting problem, which means by implementing gas. So they're like, how do we prevent a program from running in a loop forever? We make people pay per computation. And then we also generalize the Nakamoto consensus mechanism. And that was Ethereum, invented by Vitalik Buterin. And so those are the three pieces. So you have the zero knowledge proofs in the 80s and 90s, which are actually coming back to life now. And we'll get into that in a few minutes here. And then you have Nakamoto consensus from Bitcoin. And then you have the smart contracts from Ethereum. And these different innovations are all coming together in the blockchain space to try to get us to a global scale asset tracking for everyone.
Okay, and then how did these three pieces of technology play into the solutions that we have today with scaling on the blockchain? Are these technologies that we're still using today, or are these technologies that are just in the past and that are no longer being used today?
Yeah, so what's happening is, so Bitcoin, of course, is still around today, and then Ethereum is still around today, and they're both operating in parallel, and they're serving a little bit different niches in the cryptocurrency space. But what's happening is zero knowledge proofs, which are math that's been around for 30 years now, is coming back in here to really help solve some of these problems around data compression, so that you can have more information stored on a blockchain, and it's accurate with having with less data. So you can store the really critical pieces of information without overloading the blockchain and making it too packed, where we have all these really high transaction fees. So I would say, yes, Bitcoin and Ethereum still here, Nakamoto consensus still around, and what we're doing is we're taking this old crypto technology, and then it's found a production use case. And what's funny is in mathematical science, there are all sorts of math proofs that nobody uses all the time. Like it's like kind of like a joke. Like I haven't used math past what I learned in high school for forever. Like I'm never using calculus 3 in my daily life, even though that's what they forced me to go through in college. But it's funny because sometimes this math just comes in, and when it finds a production use case, all of a sudden everybody really wants to use it, and that's what's actually happened with these ZK proofs. So I think let's go ahead and kind of move in there. Before we move to where ZK proofs come in, though, we're going to take a little quick detour and talk about some of the other technologies that people are using. So those are state channels, sidechains, plasma, and optimistic rollups, and we'll try to take these in turn. So these are the ideas that were tried before ZK-Rollups kind of came back in and came onto the scene for the second time.
Yeah, for sure. So I know we covered state channels a little bit in the last episode, but give us a recap of state channels and talk about, how that was sort of the OG solution that kicked off the scaling process that we're in today.
Yeah. And so state channels very simply were a way for two people who are interacting with each other to decide amongst themselves that if we're going to do 100 transactions this month, instead of doing 100 transactions back and forth, let's just keep track ourselves of the transactions that we've done, and at the end of the month, just do one transaction to settle all of those other ones. Then what they did, so that was the big idea. That was like the idea of how this could work. And that's a really smart way to handle having a lot more transactions, people be able to do a lot more transactions on blockchains with storing a lot less data, because you're only storing one entry at the end of each month for all 100 transactions that we do. And then if we do 1,000 transactions, we still just have one entry at the end of the month between you and me. And that in computer science is known as constant size scaling, which is great because that means no matter how many transactions you and I do, we still only have to have one Bitcoin transaction at the end of the month. So it's a little bit
just to clarify for listeners too, when you say, you aggregate all of the transactions that we have over the course of a month and just have it written out once at the end of the month, that doesn't actually prevent the transactions from happening in real time throughout the month, correct?
That's correct on our own personal ledgers. So, but you won't see it on the Bitcoin blockchain. So what happens is you actually set up basically a separate ledger that's next to Bitcoin. And then we are signing transactions to each other throughout the whole month. And then only at the end of the month are we settling it. And the way that we feel confident about that state channel, which is called between the two of us, is that every time I say I send you money or you say you send me money, we're signing that message so that I have a signature from you that says, yes, I do owe you this money. So if I send you $10 and then you send me $5 and then I send you $2 and then you send me $10, we can keep track at the end of the month because I'll say, I have all these signatures from you that say you owe me this much money. And then you'll say, I have all these signatures from you, and they can be verified on chain with your private, that's the right signature for that. So you can feel confident. So, and then that makes me feel better about this outside ledger being accurate. And then to make it even more accurate, you can write little programs that will deposit money on Bitcoin inside of the state channel so that if you try to cheat me at the end of the month, I can actually use that signature you have for the last transaction you did. And then I can publish that on the Bitcoin blockchain and get my money no matter what, right? So I do have the same security guarantee as you would have on Bitcoin because I have that signed message from you. And so they're like, oh, that's a great solution. Why doesn't everyone just open up these channels with each other to pay each other? And then they can just settle once at the end of the month. And so people got pretty excited about that when that first came out because it was a really good solution for scaling. And that actually led to some other innovations like Lightning Network and a few other things like that that you hear about today. And that general principle of allow people to do a whole bunch of transactions and then aggregate it down on the primary blockchain is a very good scaling principle, but it has problems. And the biggest problems with these these state channels is that you have to have deposits like we just talked about. Because if you really want them to be secure, then you need everyone to put some money up. And then the amount of money that you put up is proportional to how much transactions you're going to have with each other. And that means that anyone who wants to participate in these side channels to make their transaction costs a lot lower has to put money in escrow every month. And that can be quite expensive. Like you may not have enough cash in your corporate bank account to float that much money. And that basically made people start exploring solutions other than state channels. And that was a gross oversimplification. And I'm sure we can get some people on here to talk about state channels because there's still a lot of research around that because it makes a lot of sense, particularly for big companies who know that they're going to be doing a lot of business with each other. That's a pretty good solution.
Right. Okay, so there's some limitations with that, which is why we have all these other solutions that you just rattled off. So let's just go down the list. The next one, sidechains. Tell us more about what sidechains are.
Yeah, so sidechains, it's basically you make another blockchain and it is just living right next to the current, like right next to the main blockchain that you're building off of. And so you could have a sidechain that's a sidechain of Ethereum, or you could have a sidechain that's a sidechain of Bitcoin and it's just sitting right next to it. And these typically will have some sort of bridge back to the main chain. And this is for bonding, like a bonded bridge. And there will be somebody that's sitting there that will kind of watch the transfer from the main blockchain to the side chain. So to make this more concrete, if you're on Bitcoin or Ethereum, like one of these major chains, you could put your money at a certain address or into a certain smart contract on Ethereum. And then once it's on that address, there's this other side chain over here that says, okay, if someone deposits money on that address, we'll give them a credit for that same thing on our blockchain over here. Okay. And then this blockchain can do a whole bunch of transactions. And that blockchain will have a lot less users than Bitcoin or Ethereum because it's made for this specific purpose. And that blockchain could even have certain restrictions around it where only certain people can use it so that it will always be cheap. Well, okay, so this sounds good because now it's like, okay, I have some money and some cryptocurrency on one of these major chains. I want to do a lot of transactions, but I don't want to pay these high transaction fees or wait too long. Let's move it over to the side chain, and then I can do a whole bunch of different interactions over there. And then I can come back to the main chain whenever I want to get my Bitcoin back or my Ethereum back, and then I can go sell it or whatever it is I need to do. So this solution is basically, if you think about it, it just comes down to the solution to not having enough room on one blockchain is to make 50 blockchains. and so that's kind of like a funny solution because what happens is you'll have a side chain that'll launch and it'll be good for a while because it'll be super cheap. And then when that side chain gets popular, you have to launch another side chain, right? And then when that side chain gets popular, you have to launch another side chain. So you have this endless plethora of blockchains that just kind of blow up. And there's a lot of projects in the space that were actually thinking back in 2015, 16, 17, they said to themselves, we're not really going to have a great solution for scaling. We think that the solution for scaling is going to be to have more blockchains. And you're just stacking blockchains on top of blockchains at this point. And I think that's a lot of the reason why we just had so many blockchains that happened. If you remember, there was Bitcoin, and then we had like Litecoin and Ethereum, and there's like a few Dogecoin and a few others. And then all of a sudden, 2015, 16, 17, I think 2017 was really the big year. You just went from like 10 blockchains to 10,000 blockchains basically overnight. And what was happening is people in the space were trying to experiment with the idea of maybe having a lot of blockchains is the solution. So what are the problems with sidechains? Well, there's the problem I just told you, which is once a sidechain gets popular, now that it's not cheap anymore, so that's not really super useful. But maybe you can solve that problem by saying this sidechain is only going to be used by these people, and so that can be helpful for you. But now you have this problem where you have to trust whoever this bridge is on the sidechain that's running it. So the security model is not nearly as good as Bitcoin or Ethereum. So if you have a lot of money and you are interacting with these sidechains, you may be nervous that, hey, this sidechain could be compromised. Someone could attack the network. It could go down. Maybe my money gets stuck. I can't get it back because you don't have the same security guarantees on sidechains that you do with Bitcoin or Ethereum. Because when you have a Bitcoin, it's just as secure as the Bitcoin network. But when you move your Bitcoin to one of these sidechains, it's only as secure as that sidechain. Because if that sidechain gets hacked, that person can take your Bitcoin. And so when sidechains became a thing, a lot of people in the space were like, this is not what we were really looking for because we want something that can be a little bit more secure than that. So, but sidechains are still around today, and so are state channels. So both of these solutions that people are using for scaling are great solutions for particular use cases. And as we'll see as we keep going, like all of these different solutions that we're going to talk about have their particular group of use cases that people are going to them for.
Got it. Yeah, it's kind of like in healthcare, like treating the symptom and not the root cause, right? You just keep building more and more blockchains. You're treating the symptom, and it works for a while, but at the end of the day, you're never going to solve the root of the problem unless you pull out the weed from its roots.
I think that's fair. But I'd also say that there are particular cases where sidechains make a lot of sense for your particular project. Like if people just want to interact with your application and you want to roll your own application-specific blockchain, then sidechains can make sense in those use cases. Really, you just have to evaluate it on what you're doing. And then, state channels also could work really well for you if you're a large corporation and you do a lot of transactions overseas. And you already know who your partners are, so you could do something like that. So, but no, they're not a generalized solution for everybody to use in the way that I think a lot of people in the blockchain space are looking for.
Got it. Okay, that makes sense. So let's talk about more solutions. Let's go to the next one. Plasma. Tell us more about what Plasma is.
So I think we should actually have I'll touch on these last couple ones, and I think we're gonna have to do another episode here where we bring Braden on. But we should really talk about Plasma, optimistic rollups, ZK-Rollups as a group. But I'll just try to touch on these a little bit here, because I know that we're gonna have Braden come on here and chat with us about these a little bit more in the future. So Plasma is a solution where I guess the biggest down draw to Plasma is that you have to have people kind of watching it. So it has a situation where it's kind of like the sidechain where you're moving these assets onto this Plasma chain, and then you have a bunch of people with watchtowers essentially that are kind of checking out and seeing if the information that's being stored is accurate. And the big down draw for both Plasma and optimistic rollups is that the withdrawal time takes a while. You could be waiting up for a week in order to get your assets confirmed off of them. And if you think that waiting for a Bitcoin transaction to go through for 30 minutes is a very long time, imagine waiting for a week. And then I think it's the same thing for a lot of traders who are looking at these solutions. If they want to trade a lot of cryptocurrency and they want to sell afterwards, then waiting for a week is not really an option for these people in order to be efficient. So that takes us next to the zero knowledge rollups, which we kind of alluded to in the beginning. And the reason why they're cool is they don't have this wait time the same way that these Plasma and optimistic rollups do, because they use those really nifty zero knowledge proofs in order to prove information on the main chain. And so if you think about, side chains and Plasma and optimistic rollups, they're really only as secure as the people who are operating those chains for you. And then also they have some issues around how long it could take you to withdraw in the case of Plasma and optimistic rollups. They scale really well though, which is great. Like you can literally store thousands more transactions on these networks than you can do on the Ethereum or Bitcoin blockchain, but you can't have it instant, which is what I think people are looking for. So that takes us to kind of ZK rollups. And at a high level here, they, instead of storing all the data on chain for everything that you're doing you're just storing a proof of what actions you took off chain. So when you want to do a lot more transactions on the main chain, you need to do some operations off chain. And when in the state channels example, we were exchanging messages back and forth off chain and then publishing once. And then side chains, you're actually going to a separate blockchain and you're doing everything there. And then Plasma and optimistic, you're also kind of doing it on this separate system where you're calculating everything. And then you have to take a withdrawal time of 2 weeks to get off. ZK rollups are actually a little bit different in that you're publishing information to the main chain, like in Ethereum in this example, and that information is all the information you need in order to identify who owns what. So if the operators go down on your state channel, like we talked about at the beginning, it's fine because you can take their last signature and you can publish it and you can get your money. If the operator goes down on a side chain, that's a problem because you can't really get the money off the side chain back to the main chain until the system is back up again. Now, maybe you can run your own servers in order to get that thing moving again. It depends on how open the different systems are to allow you to move back off. Same thing with Plasma and these optimistic rollups is in the worst case scenario, you could take a couple weeks in order to get your assets back off. But with a ZK rollup, you can immediately withdraw on the main chain if you want to, because all the information is stored on the main chain itself. All right. So if we take this back, the information about state channels are going to be stored between you and me writing our ledger off on the side. The information on the side chain is going to be stored on the side chain. Same thing with Plasma and optimistic rollups. But the information for ZK rollups is compressed and stored on the main chain, where it subtracts out all the things that you don't necessarily have to know in order to track the asset data. So, and it's stored as a math proof, which are quite large on the main chain. So instead of storing every single transaction between the two of us, like we do on a state channel, it will store the a mathematical proof that all of those transactions happen on the sidechain. And that's a little bit of witchcraft, if you like, it's a little bit of magic in how that works. But because that's published on the main chain now, you have the same security guarantees as the Ethereum or Bitcoin blockchain, whichever one you're implementing this on, without so you don't lose any security, and you don't lose any of the you don't have to wait, you don't have to add any extra steps in there for using a ZK rollup.
Got it. So it sounds like ZK rollups are kind of the answer, but I feel like there's a but coming. What's the downside to it?
So, like I was saying, the proofs are very big, right? So on the other chains, like for plasmas or optimistic rollups, they get pretty good transaction throughput right now, particularly on the plasmas, because they're basically just storing a root of all the different transactions that they did on their outside information on the main chain. So they just store like a little blip of information. They're not storing any of the verification information like you are doing with a ZK rollup. And so that's kind of the downside. And that means that ZK rollups are like a compression algorithm and not a perfect scaling solution. So if I compare them to state channels, for instance, in a state channel, if we did 10 transactions or 100 transactions or 100,000 transactions or 1,000,000 transactions, we only have to publish one thing to the main chain at the end of every month. And so that's great for scaling because it doesn't matter how much stuff we do. However, with a ZK rollup, if we do one transaction, it'll be this size. If we do 100,000 transactions, the size of it grows, but it grows logarithmically in the best case. So it is getting bigger. And when I say logarithmically, that's like a computer science thing. But it's still getting bigger, which is a problem if we want this thing to be a global blockchain. And it's getting better on the ZK rollups, where it's getting even closer to constant scaling. But it's not there today. So when you look at the ZK rollup implementations, you're looking at getting a couple thousand transactions per second on the main chain from using these technologies, maybe 10,000. If you look at something like a plasma, it's essentially infinite because you're just publishing this one piece of data. And so the problem then becomes, for the ZK rollup, how do we make it so that the amount of information that's being published on chain also doesn't grow over time? And that's where the cutting edge research is happening right now on ZK rollups. There's a couple of solutions out there that are in progress on this, that are different implementations of how these ZK rollups are built. And that's kind of where like state of the art technology is. The problem to kind of oversimplify what that problem is, you have a whole bunch of data about all these transactions that people have been doing that's not on the main chain. And how do we make sure that we can prove that all of those transactions happen like exactly how they happen, that it's 100% accurate? So that's one of the problems. We want to make sure that this proof is 100% accurate, that all these things happen the way that we said they did. And then we also want to make sure that this data that's sitting off chain, you can always find it. And that actually brings us to another piece of technology, which I didn't mention earlier, and I probably should have, and that is decentralized storage. So when I mentioned like the history of these technologies and the three major components, I said zero knowledge proofs, Nakamoto consensus, and then smart contract blockchains. I should probably add a fourth here, which is decentralized permanent storage. And I think that that's going to be a needed component for blockchains to really scale, because if you know that you have permanent storage for data that you can store off the blockchain, then you can always feel good that you'll be able to reconstruct the proofs on the main chain for people to be able to withdraw and get their assets back on these scalable blockchain systems. So it was a little sloppy in there. We went through a lot this morning. We're going to come back at this with Braden, because he's actually the resident expert here at Unstoppable Domain on plasma chains and these optimistic rollups and ZK rollups. I spend most of my time on the ZK rollup side of things, as you guys can probably tell. But we'll come back with him and talk about these other ones and fill in some of these gaps here. And then we'll get to the state of the art on ZK rollups, which are the ones that I'm actually personally most excited about. I think that's going to ultimately get us there. If you take this really fancy math that allows us to prove beyond a shadow of a doubt all of the different movements of your cryptocurrency and crypto assets that happen off chain. And then we can pair that with a system where we can feel very confident that we'll always have that off chain data stored somewhere safely. Then the amount of information you have to store on the blockchains like Bitcoin or Ethereum, Ethereum specifically is one where most of this research is being done, can be constant in size, and then or grow very, very slowly, maybe logarithmic or something. And that would mean that the number of transactions we can get done on these blockchains would go up by several orders of magnitude. And to put some numbers on it, because I know everyone at home is curious, technology today for what I would consider to be the most secure scaling solutions can very confidently get you to 50 to 150x improvement. So if you're currently paying $20 right now on chain using one of these very secure scaling solutions, I think you can get 100x speed up. And so instead of being $20, it'd be closer to 20 cents. That's where we are February 2021. And if you look ahead another 3 to 5 years, and I know that sounds like a long time for everybody, but I've been here for 7 years, so that's actually quite fast. I think we'll get another 1 or 2 orders of magnitude inside the next 2 to 3 years, and then in 3 to 5 years, we'd probably get another 1 or 2 orders of magnitude on top of that, and that will get us to global scale because at that point in time, you're able to do hundreds of thousands of transactions per second on these blockchains, which is larger than the Visa network, if not 1 million transactions per second. So we're on our way, not there yet.
So ultimately, the goal is pretty much that what we can do on the blockchain is what we can do on Internet 2.0 today.
I would say the goal of the blockchain is a little bit different because every new technology is like a little bit different than that. And it's to build a global settlement network that you can trust, but will actually work for all 3 billion internet users. So yes, the goal for blockchains is to get to internet scale, just like Facebook, has 2 billion people working on it every day and they don't have a problem. We want blockchains to work like that for all 2 billion people. And we want the transaction fees to be absolutely as low as possible. And transaction fees, I don't think will ever be free, but I do think we can get transaction fees down to be fractions of a penny over the course of the next decade. And it's going to take time to get there. But I'm a strong believer computer science will be able to solve these problems.
Awesome. Well, thanks so much, Matt. Just to recap real quick, some of the state-of-the-art solutions that we covered today are state channels, sidechains, plasma, optimistic rollups, ZK-Rollups, and the Validium off-chain data storage. We'll be back again next time with Braden, our CTO, to dive further into some of these technologies and tell you more. But thanks so much for the overview today, Matt. This was great. Thanks, listeners, for tuning in. And we'll be back again soon with another episode of the Unstoppable Podcast.